Today we give a lecture on L1 regularized least squares. As we see previously that adding L1 regularization to the regression problem will promote the solution to have a sparse solution, which means that your model can contain a smaller number of parameters. So your model becomes simpler and in terms of interpretation, it will allow you to suggest whether whether a set of predictors are significant by looking at the zero pattern of your model parameters. So in this lecture, I would like to start from this basic property of L1 regularization. The reason why the L1 penalty term can promote sparse solution is because of what we're going to see here. So I would like to start with a simple one, a scalar problem, and it's a quadratic loss, quadratic loss plus L1 penalty. Of course, the simplest form of the L1 penalty is the absolute value function. All right. Reminded the L1 norm of a vector x is the sum of absolute value of all the entries. All right. So if x is a scalar, it's not a vector. So everything reduces to this form. So if we ask you a question that, all right, if you minimize these quadratic function, the reason why I use really the quadratic function because this is the simplest form of MSE loss function, sum square error. All right. Minimizing this objective is very simple because your solution would be A, right? Quadratic. This is like quadratic function, parabola graph, center at A. So the solution must be A. I forgot to mention that please do not get confused between variable x. When I talk about statistical model, my x is the predictor, is the input variable, right? Sometimes I use x to represent mathematical function like this fx. All right, so x doesn't have that predictor meaning anymore. All right, so please look at the context. All right, so now, so everyone know that if you look at the loss function, only the quadratic loss, the solution is A. The question is when you add L1 penalty, the absolute value function of x, right? And you add some penalty parameter gamma. This gamma is positive, all right? How would the solution of x change under the presence of this term? Now I just use this plot of the graph for you to inspect a solution. So we can differentiate into three cases depending on the relation between A and gamma. A is part of the problem parameter. Okay. The first case when A is when the magnitude of A is less than gamma. Okay. For example, A is 1, A is minus 1, all right, and my gamma is 2. Okay. I plot the graph. These are two examples, the green, the blue one and the orange one. If you minimize, if you find the minimum of this graph, where is it? Panat?
At x equal to 0.
X equal to 0. And of course, how to get this graph, you just need to look at this function, all right, so that it is composed of quadratic function, right, and the absolute value function. So you're gonna need to make the sum of these two guys. But it's the parabola that is shifted, right, because it's centered at 1 and minus 1. All right, and if I move to the case 2, the case 2 is where the value of A and gamma, they are equal. All right. If you look at the orange curve, the minimum is also 0. If you look at the blue curve, the minimum is also 0. How about this one, the last one? This is case where the magnitude of A is bigger than gamma. In these examples, A is 4, A is minus 4, and gamma is 2. All right. So when you plot the graph to make the sum of two terms, the conclusion of the orange function is the minimum. Where is the minimum now, Thirawat? If you look at the graph, can you approximate it? Thirawat.
Hello ครับ okay. Around x equals negative 2.
It's somewhere around here, right? So it looks like there's a kind of the local minimum here. What about the blue one, the blue graph?
Around x equals to
Yes, Thirawat, you can answer.
around x equals to
around x equal to. Okay, I mean of course to now you see that first of all remember that without this term the optimal solution is A, right? Without this term, but then with the penalty term you see that x star is 0. Here x star is also 0, right? And even the third case, the solution is no longer 4 or is no longer 4 or minus 4. It's shifted by some value. Okay, and here, okay, we look at how to get the optimal solution. All right. You take a look at the cost function. Okay, now we consider two cases. All right. So when x is positive, when x is non-negative, right? When x is non-negative, you know that this term becomes absolute value of x is x, right? So this term become gamma x, and you can basically complete the square. You can make the sum of x minus a squared plus gamma x under the case that x is non-negative. Now, once you complete the square, you see that now my solution should be, it becomes quadratic function, right? Parabola with center at a minus gamma. So optimal solution should be a minus gamma. But because I derived this under the condition that x is bigger than 0, then x star would be this, provided that my a must be bigger than gamma. So that x star must be 0. X star must be non-negative. Okay. Of course, if that condition doesn't hold, if a is less than gamma, x star should be 0. Okay. Because the parabola f is centered at a minus y, but a minus y becomes negative value. Okay. Now, the second case is when x is negative. When x is negative, of course, now you look at this cost objective, and then this become minus gamma x, right? Because x is negative. Then again, you do it again, you complete the square, the sum of the two yellow terms. And now when you take the sum, when you complete the square, it becomes parabola graph again, but now center at a plus gamma. Then if you minimize it, you will say the minimum should be at this, right? At the center. But then with the same reasoning, the minimizer is this, given that this quantity must be negative, or in other words, a must be less than minus gamma. All right. Of course, if that condition doesn't hold, if a is bigger than minus gamma, x star must be 0 instead, because the parabola graph center at this point, right, is a positive number. So that leads to the conclusion from this analysis. This leads to the conclusion that whenever A is less than gamma or A is bigger than minus gamma, which means the absolute value of A is less than gamma, your x star must be 0. This is the same analysis. This analysis is the same as the graph we observe here. Okay, when absolute of A is less than gamma, your optimal solution that minimize this cost objective is 0. Okay. So now we have when A is less than gamma, x star is 0, right? But what about the other case, when absolute value of gamma, when absolute value of A is bigger than gamma, we have two solutions, right? Two cases. So A star, x star is A minus gamma, x star is A plus gamma. So we can combine these two cases into one representation by using the sign function, okay, sign of A. So when A is positive, right, when A is positive, this condition becomes A bigger than gamma. Your x star is A minus gamma times the sign function. The sign function return 1 if A is non-negative, return -1 if A is negative. So when A is bigger than gamma, x star is this. When A when A is less than minus gamma, right? So x star is minus A minus gamma times -1, or in other words is A plus gamma. So what I'm trying to say is these closed form solution in the yellow highlight is actually the same form as these two conditions, but it just it was written up into just one expression. We see here that the problem of minimizing this cost objective, all right, it has a 0 solution under this condition when magnitude of A is less than gamma. It also means that when gamma is big enough, remember that A is going to be your problem parameter. It's given to you. So when gamma is big, gamma has a meaning of penalty parameter. All right, it will be also up to the choice of the user as well, but you can adjust whether you want to weight this term more than this term. Okay, but when you try to weight penalize more on the absolute value term, you pick gamma to be large, then of course it will be easier to fall into this case, right? When gamma is big, the upper bound is increased, which means your solution will tend to be 0. And that is the first introductory interpretation of why the L1 norm promotes sparsity in the solution. From this simple scalar problem, we can generalize it into a vector one, because now you can generalize x to be a vector. You can let A to be a vector, right? And of course, this representation is actually the when you write it, it's going to be sum of xi, I from 1 to n, xi ai square plus gamma, the sum of absolute value in components of x, right? So when you expand, when you just express it into a sum, you will see that, oh, this is nothing, but it's in the same form of the scalar problem we see before, right? So you can just minimize according to xi separately, because this sum is separable in all xi. Right. So the optimal solution of this problem in the vector form will also can be obtained in the same way, but it's just that you interpret each expression as an element-wise operation. Okay, which means whenever the sum entries of A bigger than gamma, that corresponding entry of X would be this expression. Okay, now let me give you some example. Suppose my A is 2 minus 3, 1, all right, and my gamma is 2. My vector X would be, now we can do together. Napat. Now the first entry of X star.
0.
Let me go to maybe 2 minus 3, 1, and then 5. The first entry is
0.
Is 0, right? Napat, the second entry.
It is.
It fall into the first condition or second condition?
The first condition.
And the value is?
Minus 1.
Is minus 1? Yes. Okay. The third entry, Trung.
The second one, Asha.
Huh?
The second one.
The third
0.
one.
0.
0, right?
Yes, Asha.
Trung, the last one.
Yes, the first one.
Last one.
1, Asha.
This A is bigger than gamma, right?
Yes.
So
5 3, Asha.
Yes, is 3. Okay. So this is an optimal solution of this simple problem. And you see that there's some 0 occurs here. So whenever this condition is satisfied, that means if I increase gamma to be 5, what happened? My X star would change, right? Theta what? If my gamma is 5, what happened?
All of them would be 0.
All of them would be 0. That's what I mean. When I increase the penalty parameter, right? So this condition would be easier to satisfy because A is a problem parameter given by description of your application. So when you increase gamma, the solution will be like getting sparser until gamma is large enough, right? All the solutions are 0. So this is why L1 regularization is included in regression problem to promote sparsity. Maybe I can skip to maybe later. Okay, there's another way to express to interpret these characteristic of L1 solution can be done by looking at the contour of L1 unit ball as well. Okay, but let me state the problem that, okay, when people have observed this benefit of L1 norm, right, the first problem that we see here is that how about adding L1 norm penalty into the least square problems? Okay, so this is called L1 regularized least square. It had other names in the literature as the Lasso problem or basis pursuit. The meaning would be that, of course, the cost objective consists of two terms. The term with the quadratic loss or the least square, and the other term is the L1 penalty. Of course, we mentioned before when you minimize the sum of two terms, right? Which means you want these two functions to be minimized at the same time. You want the sum to be minimized. But as you have some gamma that is the constant, we call it penalty parameter. This gamma plays a role of how you're gonna trade off between minimizing and f and g. Okay, if gamma is big, which means you focus more on having a sparse solution in beta. And when in that situation, beta would be very sparse, right? Gamma is big, beta is would be very sparse. In that case, what you a trade-off would be your model would have a larger bias. Okay, I shouldn't use this. Because, I mean, of course, the optimal beta without penalty, the optimal beta would make the pink term minimize, right, with the smallest residual. But now you have, you want to regulate beta to be something else, to have some sparsity. That beta is no longer optimum in the sense of least square. And of course, the pink term, all right, the bias in here would be increased. And of course, on the other hand, if gamma is less, your beta would be, of course, dense, but the model bias would be less. Okay. In terms of looking at this problem mathematically, there is no analytical solution, unlike least square. But we can solve it efficiently. It falls into a convex problem, so we have a very efficient algorithm to solve. All right, and one thing is that when you have the L1 norm, the problem, the cost objective is non-differentiable at beta equals 0. Okay, so even though there's some concern, right, in the derivative here, but because the problem is convex, I would say solving this numerically is no longer a problem anymore. From statistical point of view, the meaning of L1 regularized least square can be interpreted as a maximum a posteriori estimation or map when beta has a prior distribution as Laplacian. Laplacian distribution is something that has the form of this, right? Is exponential family function, but the exponent term, all right, unlike Gaussian, the exponent is negative or quadratic, right? For Laplacian, the exponent is negative of absolute value of beta. So with the map estimation, it means that you have some prior knowledge about beta that you would like to add in the estimation process. So in this case, I would like that prior knowledge is about, I would like beta to have sparse solution. Okay, here's some results to get observation here. I solved the Lasso problem. Still contains a mistake, sorry. My big N, the number of samples is 100. My number of predictors is 500, all right. I solved this with Y, solved the previous, this is a description that I solved. I use gamma equal 0.2, then I get beta Let's see, because I thought I already fixed it. Okay, now. So this is a solution of L2 regularization. So my beta will have beta 1 until beta 500, right? I have 500 elements. So I just basically plot the histogram. This plot is a histogram of beta. And then when you see, so it's like the distribution is widely spread. Okay, some of them, of course, some of them is 0, but some of them are non-zero. On the other hand, if you look at the histogram of L1 regularized solution, so what do you see here? All right, the frequencies here, I think I normalized it to 1. All right, so the scale from 0 to 1. So what does it mean from this graph, Tira Watt?
For L1 regularization, they are smaller beta.
Yes, so 80%, right? Around 80% of 500 elements. 80%, I can say, oh, most of them. Most of them is 0. So L1 solution is sparse. Okay.
อาจารย์
Yes.
I have some question. Is this imply that non-zero beta is cannot be more than n, right?
Cannot be more than n. Which n? Big N here?
Big n, yes.
No, it's not about big N. I have 500, right? That's P. I have 500 elements in the vector beta. Okay, so I basically plot the histogram of beta to see the distribution. It's not the statistical distribution. It's just that I want to see the range of beta, the range of entries in the vector beta. Okay, so from this, if you look at the graph, right, you see some tails here, right? Some entries of them has a magnitude of 0.2 minus 0.2. Now, I at this point, I don't justify yet. If we can say something about, if we can guarantee about, mean and max, I don't justify that right now. But what I can conclude from here is that 80% of 500 elements is 0. Is here at 0. So it's not about this big N.
Okay ครับอาจารย์ Thank you.
Okay. People also solve the Lasso problem, but in different formulation. All right. Here we represent similar form of L1 regularized least square. So instead of solving this, okay, L1 norm of beta 1. You can also consider this penalty term. I mean, previously is added as part of the objective function, but now this similar form put the L1 norm of beta as a constraint. So with this formulation, it says that I want to find beta that minimize my 2-norm residual error. So this is the least square sense, right? But I also have constraint that my beta 1 should have a limitation on the L1 norm. And that limitation is specified by a scalar t. T is going to be given by the user. Okay. So in terms of optimization, one thing you should know is that everyone know that so suppose this is my on this plane, this is the on the space of beta where you can find, right, what's the good candidate. And these like ice cream cone that represents what the surface of quadratic function. Okay, so when you perform a least square, so you want to find a beta that give the minimum of this loss function, right? But then what it means by having this additional constraint is that now I have constraint. I want beta to be restricted by you know, this norm budget. So it basically means that instead of being able to search over the orange space, now I'm limited to only search within this area. Okay, so the L1 norm of the L1 norm. So if I restrict down to R2 space, right? So the one norm of beta would be the sum of two elements, right? In R2 case. Okay. So if I have a limitation, on L1 norm given limited by t, if I plot this region, right? So that region would look like this. So this is to plot the graph of this. It would be a region where the side, this is the side, right? The sides of this region is just described by the linear function. Okay, this is going to be t minus t, all right? So so what I represent in here is that now when you have L1 regularization, but in this form, all right, it means that now you only allow to look at the green space and what candidate in the green region that gives you the minimum value of this surface of this cup. Now you will see that, of course, minimizing this formulation, the obtaining the resulting residual, okay, would be bigger than the optimal residual obtained from least square framework. Okay, because now in this case you only look at the candidate in this green area, right? You have limitation. Of course, the best way you can do is going to be worse than the scenario where you can search over all the whole space. Okay. So the formulation on this description, all right, this is called the Lagrangian form. The Lagrangian form of this problem. Okay, so this is a term in optimization. These two forms, I mean, in terms of numerical method to solving this form or solving the Lagrangian form would be about the same. All right. The parameter t in this problem and parameter gamma in this problem has some correspondence relationship, but they are not the same values. Okay. Now we can take a look at the observation at the solution path. The solution path is actually the optimal solution beta when you solve the Lasso problem by varying penalty parameter. Okay. Now we compare between Lasso and ridge regression. Remember, Lasso is L1 regularization, ridge is L2. Now I solve with beta is in RP, which in this problem is P equal 5. So beta has 5 entries. And what we do is we solve the Lasso for many values of gamma. For a fixed gamma, right? For a fixed gamma, of course, your beta is, for example, 2, 5, 4, 0 to 1, for example. All right, I have 5 entries. So those 5 entries, so if I look at one entry, so there's going to be a solution path as a function of gamma. From this graph, what do you see? What do you see? As you, as gamma is big, as gamma is big, of course, when penalty parameter is big, what happens is solution will be sparse, right? So you see all the solution parts, all entries, now it tends to 0. When we see here at this point, it basically means that when gamma is this small, gamma 1, some of the entries are already 0, but these ones are still non-zero, right? And then what? When gamma keep increasing, of course, more entry will be 0. Some of them can become non-zero again if you look at this graph. Now, in comparison to the ridge regression, what do you see? Oh, I would like to probably make a note here that 0, yes, 0 is around here. Okay. So you see that when gamma is big, who can give me the closed form solution of ridge solution? Panat, can you give me that? Ridge. The closed form solution is Panat.
X transpose X plus gamma I inverse X transpose Y.
Okay. Okay. If you look at this expression, now Sukit, what happened when gamma is big?
The beta is small.
Oh, gamma is big, and this is inverse.
Diagonal of X transpose X plus gamma I is large, so the inverse is small, right?
Yes, like conceptually, like of course conceptually when gamma is so big, like think about like million, all right? Of course these inverse would be very small, right? The inverse would be very small, or you can, I mean mathematically, you can think of this as so this term, think of this as a two term, right? So the norm of beta would be, let me write it into like a rectangle with a triangle. The norm of beta would be bounded by the norm of the rectangle times the norm of the triangle. Okay, submultiplicative property of the norm, which means if gamma is so big, this matrix, rectangular matrix here is going to be small. Of course, the norm would be small, right? So the norm of beta would be small. And then that's why we see that the trail, all the tail here, beta would have a smaller magnitude. But the thing is, the main distinction between the ridge solution and the lasso solution is that they are not exactly 0 if you look at this closely, right? Unlike lasso solution, it becomes exactly 0, the component of beta. Okay, so the resolution converge. Eventually they are 0, but there's some small entries instead of being exactly 0. Okay, now we can explain the sparsity of the solution of lasso again. If we take a look at the problem in the form of you minimize this least square objective under the constraint. This is subject to, right? Subject to for the rich problem, the constraint is the 2 norm of beta less than t. For the lasso, is 1 norm of beta less than t. Okay, so graphically we can represent it in this. The constraint, so what I'm drawing is the norm ball constraint. For 2 norm, the set of beta that the 2 norm of beta is less than t, of course, is going to be a circle, right? The region in the circle. And for L1 norm, it's going to look like this rotated box, right? The red one, what is the red one? The red one is a contour, the contour of the quadratic loss, because it's quadratic in beta, so the contour looks like ellipsoid. Okay, so without this constraint at all right, your least square solution is here, right? Is where your the contour, at the point here, it corresponds to the minimum value of the loss function, the quadratic loss function. Now, when you have constraint, it would mean now you can only look in the choice of beta in this set, in the blue sets, all right? But you're gonna look at the point where it's correspond to the possibly minimum objective value. Okay, so basically we look at the contour, and whenever, of course, when the contour is bigger, it means that the cost objective, the quadratic objective, is bigger and bigger, right? Then you find where the contour, the first time, not the first time, you try to find the smaller contour, but the contour also need to touch the constraint set. So in this graph, it touches here. So in this particular example, your optimal beta would be 0 and 1. On the other hand, with this graph, your beta is this vector. What I want you to notice is that in the L2, in the rich penalty, all the entries of beta, all the 2 components are non-zero. Now, this is why the Lasso solution is sparse, because if you look at the contour will hit this L1 normal set. It's going to be more likely that it hits the vertex, right? Of course, I mean, there's a chance of there's a chance that it can hit on the side as well, but of course, whenever it hits the vertex, and that's how you get a sparse solution, because one of the entry is 0. Okay. On the other hand, for L2 normal, all right, whenever, I mean, more chance is more likely that when you hit the 2 norm ball, that's gonna correspond to non-zero solution. Okay. Now we take a look at the now we compare some property of the Reed and the Lasso solutions. Now we solve the problem, and we solve it under 2 conditions. That's the 2 conditions about the ground truth beta. The first one is beta is dense. The other one is beta is sparse. And what I plot, okay. Now I would like to slowly zoom in. On the left graph, what do we see? Okay, now I plot MSE. Okay. And the MSE that I plot here, the orange, the purple one, this is the test MSE. Okay. Now, remember that when gamma varies, when gamma is big, right? Beta is sparse. If we take when beta is sparse, of course beta is your model parameter. When beta is sparse, some of the entries are 0. So if you look at the corresponding model, my x hat times beta hat, right? That's my predictor 1 times regression coefficient 1, and so on. Okay, so if some of them is 0, I mean, in terms of model complexity, your complexity is less or more. True. True.
Less, Ajahn.
Yes, your model complexity is less, right?
Yes,
Beta is sparse means that you actually use a fewer numbers of parameters. Now you have more compact model, which means with this scenario where you vary gamma is the same as you're talking about varying model complexity. But it's just the direction is the other way around. When gamma is big, the complexity is less, right? Okay, everyone follow that? When gamma is big, complexity is less. When gamma is small, beta is dense, right? Dense, your model is dense. You use more parameters. So we can say, model is more complex. So first of all, if you look at the variance and square bias, does it make sense to see things like this? First of all, variance is smaller as gamma is big because Panat.
Because it's high bias. What do you mean?
I mean, of course, we know that variance and bias, they are complementary to each other, right?
Yes.
But the actual reason of why the variance is smaller as gamma is big because the model is, this is in the this is in what? This is in the proof. The proof that I didn't prove in the class. The proof
because
that I
it's
have.
less correlated, Ajahn.
Yes.
Because it's less correlated, Ajahn, right?
It's not about less correlated. It's about because the model is less complex. Yeah. I think you should see the proof. All right. I didn't have time to explain all the mathematical proof. Remember that we have the slide here. We have M1 and M2, right? And I say M2 represent a complex model, M1 represent a simple model. Complex mean have more parameters. And we show mathematically that the covariance of parameter of complex model would be bigger. This is bullet 2, and the proof, mathematical proof is here. But on the other hand, this is a drawback, right? Number 2 is a drawback of complex model, is that which means that the model parameter itself is more unreliable, less predictable because it has more variance. But a good thing is that your complex model would have a lower MSE than the simple one. Would have lower bias error. So so I want always keep this in mind. trade-off between complex and simple models. Where can I get back? In here. Okay. So which means what? When gamma is big, your model is simple, right? Less complex. So that's why variance is smaller. But on the other hand, a drawback is that the bias is bigger. Okay, that's the thing. And another thing I want you to observe is that if you plot the test MSE, okay, now you plot the test MSE versus gamma, but gamma has a connection of with the complexity. So you will see that there would be an appropriate amount of gamma, which means an appropriate degree of model complexity where your test MSE or the generalization error is at minimum. Okay. All right. That's the first observation. Now let's take a look at this comparison. Now I would like you to look at here. When the true beta is dense, okay, so the problem is the thing is when you have lasso problem, right? Of course, when gamma is handed to you, you can find a solution, but in the real application is what value of gamma should I use for this data set? I know that, of course, I use different values of gamma, I would have different characters in my solution. I use small gamma, my solution is dense, right? Harder to interpret. If I use big gamma, my model is going to be, we will contain only a few number parameters. I can interpret better. But then what value should I pick? And this is one way you can do, which means that you can plot, right? Plot the MSE on another data set, the one that you don't use on the training. And then you look at the test MSE that corresponding to the minimum one, and you can pick that gamma to be the one you should use. Because it means that is the value that I get the minimum generalization error. All right, but I would like, what I wanted to say is that if I just mark the value of gamma here, and now I look at the other case when my true beta is sparse, it turns out that my best choice of gamma is perturbed a little bit to the right-hand side. So what conclusion can we draw from here? Napat?
When the true beta is sparse, the gamma is higher than the dense case.
Which further means?
The model is less complex.
So it means that the solution lasso from the two cases, in terms of denseness of the solution, which means if you select gamma according to this scheme, pick the gamma that give me the minimum generalization error, it also give me a very reasonable solution, because when my ground truth is actually sparse, right? My ground truth parameter is actually sparse. My selected gamma is also bigger, which means my lasso solution would be also sparse. All right, that's I mean you can do, like, you can reproduce this graph by a simple implementation of lasso and see. Now, okay, that's how we compare between the two cases of ground truth. Now I would like you to move to the right hand side. Okay. On the right hand side, I want you to compare between the dot and the solid line. And that's where we compare the rich and the lasso solution. Okay, If you look at the test MSE, okay, you will see that the test MSE, the dot mean the ridge, right? And the solid is the lasso. They are about the same. They are about the same test MSE. But on the other hand, if we move further on the lower plot, what do you see? Oh, sorry, the wrong one. I should label the purple curve, dot and solid. Kilowatt. Can you compare the test MSE between the ridge and the lasso? Which one is less?
The lasso is less.
The lasso seem to achieve a lower test MSE. And again, these two cases are different by what? By the ground truth assumption, which means that you can see a benefit of lasso solution. That benefit is it gives you a lower test error when the ground truth parameter is actually sparse. It's also sparse. Okay. Now I would like to talk a little bit more about mathematical property of lasso formulation, and this is how we compute it, and I mean a closed form solution in a special case. Okay, when we look at the lasso formulation, first of all, it's a quadratic programming. It's a convex problem as well. Quadratic programming, what it means is that it has quadratic objective. This L1 norm thing, there's a way in optimization where you can reformulate it as a constraint. Okay. When X is not full column rank, remember that the least square problem has a motivation from solving overdetermined linear equation. So when the regressor matrix is tall, all right, and the condition for the least square solution to be valid is when X is full rank, right? And when X is tall, full rank would mean full column rank. When X is not full column rank, that can be okay when you have when you have what? When you have collinearity, right? What is a collinearity again, Sukit?
It means some of the predictor has correlated.
Yes, some pair of predictors are correlated, and that makes what? Some columns in the regression matrix dependent, right? And which further mean X is not full column rank. Or, okay, when X is not full column rank, that could be from the problem where when X is tall, but you know, you have collinearity problem, or in some application that turns out that you have more predictors than samples, which mean when your regressor matrix X becomes fat. In that case, the fitted value of the least square is unique, but your solution is not. Your solution is no longer unique. That's a property. That's one fact that you have to keep in mind. We have this result proved by Hasty that when X is in general position, this also involve the definition of this property as well. That you can check it out from the book. That when X has a general position, the solution lasso is unique. Now let's take a look at the optimality condition from the convex theory. it involves the subgradient calculus. Okay, if I can say in short, the Lasso problem, the first term is differentiable because it's quadratic. So when we take the gradient of the quadratic term is this, right? And then you apply the chain rule, and that X transpose. On the other hand, the second term, the second term here is non-differentiable for all beta. Okay, and then that when we enter when we introduce the definition of a subgradient. So a subgradient of the L1 norm function, that's going to be a sine function, the sine function. It's going to be the sine function when beta is non-zero. Okay, because what? Because the L1 norm, remember that is the absolute value of what? The absolute value of n components. So whenever beta is non-zero, if you take the gradient respect to each variable, right? And that means that it gives you the sign. Because the absolute value of some component of a component is equal beta itself when beta is positive, is equal to minus beta k when beta k is negative, right? So when beta is non-zero, when you take the gradient, so it's going to be either 1 or minus 1. All right, so that's why I say that, oh, in this first case, the gradient, the subgradient is the sign. Now, when beta is 0, okay, what we call the subgradient, there's some more detail, but I don't want to go in there. I say that the subgradient of the L1 norm is going to be the subgradient at component I is going to be any number between minus 1 and 1 when beta I is 0. So it's more like when beta is 0, which is on the right hand side, right? The slope is 1, so you say the gradient is equals to 1. On the left hand side, right, you look at the graph, the slope is what? The slope is minus 1, so you say the subgradient is minus 1. But when beta is 0, okay, the concept of the subgradient is to find any linear, right? Any linear curve that support your function at that point. So what we see here is that any linear curve with the slope between minus 1 and 1 can support the curve of absolute value at when beta equal to 0. So that's the concept of the subgradient. All right. From there, we can compute the Lasso solution with one predictor case because the solution can be obtained in closed form. In order to do so, I would like to further standardize the problem, which means I'm going to add big N here. Okay, that doesn't change the problem in terms of optimization. So when I introduce like some factor here, big N, that means that the corresponding gamma would be a little bit different, all right? Okay, now I'm gonna standardize the problem, which means I'm gonna remove the mean in the response, all right? Or what we can say, you make the predictor and the response centered at 0. And then normalize the predictor so that the variance is 1. And we use one predictor only. Okay. All right. The optimality condition that you see from this condition, now it reduces to this. Okay. Or you can see that if I take the gradient of this cost objective, I would get 1/2 1/2 over n, and summation of I from 1 to n, right? 2 times yi minus xi beta, and then times chain rule, right? Chain rule, and then times minus xi. Okay. And then the other term, when I take the gradient, I know that this term is non-differentiable. So the term here, I use the subgradient of absolute value function. Okay. So with this notation, I can arrange, you can simplify all of them. And on the right hand side, I represent it as 1 over n. This is inner product between x and y. Okay. And again, my y would be y1 y2 and 2 the samples yn. Okay. Now from here, my g, which is a gradient, subgradient of the absolute value function, with the note that g is going to be the sign, right? When beta is non-zero, g can be any number when beta is 0. Now, the reason why we in this formulation we put big N explicit here in the formulation, because from the optimality condition you see the row of data samples here in the box. Now let's take a look. Now, okay, now I'm gonna, let's see, now I'm gonna move things around. Oh no, not the other way around. So I'm going to write these guys minus beta equals to gamma g. Okay. So if what? Okay. What do we see? So when when beta is non-zero, right? When beta is non-zero, so this equation turns out to be what? My g would be the sign of b, right? Would be non-zero. Would be something either 1 or -1. Now we can hold on. How can I explain to this conclusion? Okay, now take a look at the first case. Now, so what I'm trying to say is that optimality condition is actually equivalent, right? Equivalent to these 3 cases. They are the same. Now let's take a look one by one. Okay. If this, inner product between x and y is bigger than gamma, so what happened? Okay, now I should write it on this. Now it'd be better to write it in this way. Okay. All right. So if of course on now. If 1 over n, okay, is bigger than gamma, what happened? Which means your beta can be 1 over n x inner product with y minus gamma, and that quantity would be non-zero, right? Which means at that point your g becomes 1. Everyone follow this? No? Yes or no? Panat?
I'm
Confused?
confusing a little bit.
Okay, now let me repeat it again. Okay, so this optimality condition says that it depends on G, and G also depends on the optimal B. All right, if the optimal B is non-zero, G is the sign. Okay, if the optimal B is non-zero, G can be any number between -1 and 1. All right, so then I'm trying to relate that the optimal condition in the yellow box, all right, which looks like, oh, I don't have the closed form, I don't know what the closed form is, but it turns out that it's equivalent to the pink box here. Now I'm trying to verify the pink box for you that it satisfies the yellow box. Okay, now by writing, now I'm writing the things on the yellow box again, and just move around. Okay, now I look at the first case. Okay, when these conditions hold, okay, I would like also to add that the condition on the right hand side are conditions on the problem parameters. It's something that you can evaluate or check when the data are given, right? Because it's only involve x and y, predictor and the response. And the threshold gamma also given as well. Okay, now the first case, let's look at the first case. When this guy is bigger than gamma, right, I can set beta equals to this. Because, and that also fulfill this yellow box, right? Because when this condition holds, my beta would be what? Would be bigger than 0, would be non-zero, right? So when my beta is non-zero, my G would be what is it? If my beta is
positive, is 1.
Yes, my G is 1, right? So it satisfies optimality condition. Okay, now let's move to the next case. The one that is easy is going to be the third one. What about the third one? If my this condition is less than minus gamma, I say I can set my beta to be this plus, right? This plus. And then so when I do it this way, what's the sign of my beta? With this condition, it also means that inner product between x and y, if it's less than minus gamma, which means that quantity must be what? Negative or positive? Negative, right? But it's less than minus gamma, so my beta would be
also negative.
Negative, right? Strictly negative, which means if I set beta in this way, of course the sign of beta would be what? Would be
negative.
Yes, minus 1, right? And as you can see from here, my beta that I express in the green term satisfy is the same as optimality condition when G is minus 1. Okay, now the last one is when what? when now the pink one, when the inner product of these two guys is less than gamma. Is less than gamma. What do we have? In order for these to hold, beta would be 0, right? Because when beta is 0, gamma g equals 1 over n inner product between x and y. All right? When beta is 0, optimality condition suggests this, right? And then if you put the absolute value of this guy, all right? And then because when beta is 0, g is between -1 and 1. So absolute value of g is less than 1, which means 1 over n, the absolute value of this guy, right, which is equal to gamma, absolute value of g would be less than or equal to gamma. And that is the what? That is the second case. All right, is it clear now? So in conclusion, for one predictor Lasso formulation, okay, with this representation, the solution in closed form is in closed form. And if you look at the closed form solution, and particularly looking at the second case, it would mean that when you compute, this is kind of inner product between x and y, right? Is this kind of a correlation between predictor and the response? It less than the penalty parameter. Here, your solution would be 0. And this mathematical expression here, we just give some name. This is called a soft thresholding operator. So what it takes is that you just need to compute correlation between x and y, right? And description in the blue box, I just use the notation S of gamma, which is the soft threshold holding parameter. And you can say in short that whatever input z is, all right, compare with the threshold gamma. So this is the plus term. The plus term is what is the plus term is the operation that you compare with 0, and I mean it's this function max and x and 0. Okay. So the soft thresholding operator can be sketched in this graph. Okay. When it exceeds the threshold, this looks like linear. All right. And there's a range here specified by gamma. All right. If this guy is less than gamma, it returns what? It returns 0. Okay. So solving Lasso's formulation for one predictor is very easy if you look at this one, right? Just compare compare this with the threshold and then return whether it's basically arithmetic operation. Okay, probably we can I mention this real quick that in practice, all right, in practice for many predictors, okay, you have regressor matrix, right? Regressor matrix. So what you do is that center each predictor at 0, basically remove the mean, and each column has unit variance, okay, because when in the original form of the regression, it has an intercept term, right? But in the Lasso formulation, we don't penalize the interception term. We only penalize beta 1 because we would like to interpret the meaning of, beta k is 0 means that xk is not significant. So no intercept term. If you have no intercept term, so we center the response instead. We center it at 0. Remove the mean. Okay. And what I should, okay, so I would like to mention that this is the standardized formulation, and with the factor 1 over 2n here, this is the standard one that most of the libraries refer to. In MATLAB, we have a Lasso command. In R, we have grmnet. In Python, you can look at the scikit-learn with the linear model, right? All these library, in terms of numerical implementation, they use different algorithms. Okay, they use different algorithms, but all of the algorithms there rely on the soft thresholding operator, which means that the soft thresholding operator just comes into place because of the optimality condition of the Lasso formulation. Okay. I think, all right. Yes. Okay. When I assign the problem, the homework problem, so you can call this library, and then what you need to enter is, of course, you need to enter X and Y. If you want to solve the lasso for a specific gamma, you need to enter gamma. But if you want the command to compute the solution path, then you would like this, right? Solution part. You need to tell them, you need to tell library, okay, how many points of gamma I want. Or if you want to select gamma according to some rule, like the one that minimize the test error, things like that. So there's going to be a cross-validation process that that MATLAB or any library, any language also provide as well. Okay.